In this lesson, I will talk about inverse trigonometric functions. Specific objectives of this lesson are evaluate and graph the inverse sine function and evaluate and graph other inverse trigonometric functions such as arcsine and arccosine and arctangent, and then evaluate compositions. So first thing we're going to do is we're going to recall what it means to have inverse function. So this is something I talked in my previous videos, and as you may remember, for functions to have inverses, it must be one-to-one. That is, it has to pass the horizontal line test. So we previously talked about how to observe if a function has inverse or not. We need to know if the function is one-to-one or not. The way we do that is we apply the horizontal line test. So in this figure given, you guys realize we have the graph of sine, and then what we're interested in is we're interested in knowing whether sine function is one-to-one or not, right? So we know that sine function has this pattern that goes on both positive infinity and negative infinity. And so if we have a line, a horizontal line like this, you guys realize that this line will cross the function at many points. So it intersects more than one for sure. And you may remember this is no good. So what that means is sine function, as with this original domain, you guys realize the domain of the sine function is any x, any negative infinity to positive infinity, and then the range is, you guys realize, it's always in between -1 and +1. So then with this original sine function, we're going to realize that it does not pass the horizontal line test. So it fails the horizontal line test. What that means is sine function as its original domain is not one-to-one, and therefore it does not have an inverse. However, if we decide to restrict the domain to the interval going from -π/2 to π/2, so let's go back to the graph. You guys realize what I'm doing is I'm restricting the domain from, let me erase all this, from negative infinity, from -π/2 to π/2, right? So only looking at x's from here to here. And then, so now what I did is that I changed the domain. Rather than from negative infinity to positive infinity, I'm only going to consider -π/2 comma π/2. So you guys realize if we only do that, then the function just becomes this purple curve. And you guys realize this curve will pass the horizontal line test, right? So if you're interested in knowing that, so you can draw some horizontal lines like I'm kind of doing here, you guys realize it's always going to pass because I'm ignoring the rest of the function. I'm only focusing on that purple area because I restricted the domain. So this is my restricted domain. Okay. So then we know that the following properties is going to hold. So on the interval from -π/2 to π/2, the function is increasing. As you guys remember, that purple thing is always increasing. And this interval sine takes on its full range of values. You guys realize the y values here are going to be from -1 to 1. So range is going to be the same in that interval. And lastly, the sine function is going to be one-to-one. So it's going to have an inverse. So next thing we're going to do is we're going to define what that inverse is. So again, the restricted domain, in that restricted domain, the sine function has a unique inverse function, which is called inverse sine function. And we generally denote that function by y equals arcsine, or we'll use this notation where we have this like -1 thing right here. So this is basically consistent with the inverse function notation that you saw before, where we had f inverse x. So the arcsine x notation, we read it as d arcsine of x. and this comes from the association of central angle with its intercepted arc length on a unit circle. So arc sine means the angle whose sine is x. So both notations, arc sine x or sine inverse x, these are all valid and you can choose any of them. On the figure, you guys can see how the arc sine function looks like. So this is the new curve that we know for arc sine. You guys realize the domain of this function now is going to be from x's from -1 to +1. So all these x's will be used. So domain is -1, 1. So the range of this function is going to be, you guys realize we look at the y values, so minimum is -π/2, and then maximum we're going to get π/2. So you guys realize this is for my arc sine function. And remember, for my sine function, I had the domain, restricted domain, which was from -π/2 to π/2, and then my range is -1, 1. So this is my regular sine function. So you guys realize because these guys are inverse, they're going to have switched domain and range, right? So the domain for sine becomes the range of arc sine, and then a range for regular sine, which is -1, 1, becomes the domain of arc sine. Because these guys are inverse functions, we have that inverse relationship going on. Okay, so one input of one becomes the output of the other. Same idea that we saw before. So here I have the formal definition that you can read. Next, I'm going to do an example. So what we're going to do is we're going to evaluate the inverse sine function. So question says, if possible, find the exact value. So what we're going to do is we're going to compute arc sine -1/2. So what this means, right? So you guys realize -1/2 is input for the inverse sine function, right? Input for arc sine x. So this is my input. So this is going to have some output probably that I don't know. So because I know that sine function and arc sine function are inverses, the input for this must be the output for this one, right? Must be the output for this one. And similarly, input for the sine function must be output for my cosine or for my arc sine function. So I know that relationship exists. So what we're interested in is we need to find output for arctangent, right? Or arc sine, I mean, arc sine -1/2. So we need to find the output. So what that means is that we should be finding, so we need, let me write it here. So then we need input for sine such that it gives output for arc sine, right? Because of that relationship, we need to find input for sine such that it gives output for arc sine. So the way we find that is we think about it. We're like, all right, what angle? So then you ask the question, what angle gives sine x equals -1/2? So what angle I should be using, what x should I be using, what angle should I be using so that sine is -1/2? So to find that, you can go back to unit circle and then take a look where sine function is -1/2. And then what you will realize is that it's going to become -30 degrees or -π/6. So we find that information from unit circle, right? So from our knowledge from unit circle. So -π/6. And then one thing we need to make sure is whether this -π/6 is within -π/2 and +π/2. And we know that is true. So what that means is that this this value is going to be in the output. So because you guys remember, negative pi over 2 to pi over 2 is going to be the range for my arcsine function. So I need to make sure that the input for sine is in that range. So because it's in that range, we're going to be like, okay, cool, negative pi over 2, pi over 6 will work, because that will, sine of that will give you negative 1/2. So what that means is that arcsine of this must be then negative pi over 6. Okay, so that's how we figure it out. So I'm going to do another example, part B. Part B has, again, arcsine square root of 3 over 2. So this time I'm having arcsine square root of 3 over 2. Okay, so we need to find this value. So then I need to ask the question, what angle x gives sine, because I need to look at the other function, sine square root of 3 over 2. So this is the question you need to answer. So the way I can answer that is, again, I can take a look at the unit circle and then see the angles that give you square root of 3 over 2. What you're going to realize is then it has to be pi over 3 or 60 degrees, because sine 60 is always square root of 3 over 2. And then the thing that I need to make sure is whether this is in this interval negative pi over 2 comma pi over 2. Then I know that is true. So then I'm going to say, well, then arcsine square root of 3 over 2 has to be equal to that angle we found for sine, which is pi over 3. So then part C, you guys realize, has arcsine 2. So this is not possible because we cannot find sine such that, or we cannot find x or angle such that sine of x equals 2. So you guys realize this is not possible because the range for sine function is always from negative 1 to positive 1. So sine itself cannot take bigger value than that. So for that reason, it's not going to be possible. So next, we're going to take a look at other trigonometric functions. So you guys realize cosine x looks like the graph here. And because it has that periodic behavior as well, it's going to fail the horizontal line test, right? Like if you try to draw horizontal lines, so you realize it fails because it crosses the curve multiple times. So it fails the horizontal line test. For that reason, we have to restrict the domain of cosine. So the restriction we apply is going to be from 0 to pi. So we restrict the domain. Restricted domain is going to be 0 to pi. And when we do that, we're going to realize that the curve that we get is only going to be this purple area. So this purple curve is what we call inverse cosine function. The way we denote that is similar to arcsine. So now we use arc cosine, or we can use this notation with the -1 exponent. Okay, so very similarly, we're going to define an inverse tangent function. And then we're going to restrict the domain of tangent to be negative pi over 2 to pi over 2 and positive pi over 2. And then you guys can see on this table all the domain and ranges we're using for the inverse functions. And then finally, the graphs of the 3 inverse trig functions are shown here. This one is arcsine, arccosine, and arctangent. So again, we get these inverse functions by restricting the domains of the original functions. Lastly, I'm going to do one evaluation problem for the other inverse functions. So I'm going to take a look at arccosine square root of 3 over square root of 2 over 2. All right, so the way I'm going to find that is, because this is going to be equal to some x, right? So this is going to be some output I'm trying to figure out. So then the thing that I need to figure out is I need to find angle x such that I'm going to look at the inverse of arc cosine, which is just cosine, such that cosine x is going to be equal to square root of 2 over 2. So I need to find what angle gives me that, right? So the way I find that is I look at my unit circle and I realize that pi over 4 or 45 degrees will give me square root of 2 over 2. So that means is that this guy must be cosine x. So then the thing that I need to make sure is whether this guy pi over 4 is in the domain of the sine and therefore range of arc cosine. So go back and find the range for arc cosine. You guys realize the range for arc cosine is 0 to pi. We know that pi over 4 is in the range. So we feel comfortable in saying that then this output value must be pi over 4. Next, we're going to take a look at arctangent. So we need to find arctangent 0. So we're going to think about x for tangent that gives you 0. So we know that tangent is 0 when angle is 0, because we realize tangent is sine over cosine. When sine is 0, then the whole thing is 0, right? Because tangent equals sine over cosine. If sine, the top is 0, then the whole thing is 0. And bottom cannot be 0, right? Cosine cannot be 0 because that will be undefined. So sine has to be 0. We need to find angles that make sine 0, and that angle is going to be 0. And we know that 0 lies in the range of the arctangent function, which is negative pi over 2 comma pi over 2. So then arctangent 0 must be 0. Lastly, part C has arctangent negative 1. So we need to find angle x such that tangent of x equals negative 1. So we're investigating when the tangent function is negative 1. So you take a look at your unit circle and then find what x angle you get. It's highly likely negative pi over 4. So then you use that negative pi over 4. You make sure that it's in the range. And because pi over 4 is smaller than pi over 2, then it is true. So then we're going to say, well, arctangent negative 1 then has to be pi over 4. So the result of this has to be negative pi over 4. So that's all I have for this video.